Now, we will now come to the more interesting part. I mean, this was interesting too, but we will come to the even more interesting part of the constraint satisfaction literature, which is constraint propagation or inference. Okay. And the first idea that we will study is the forward checking idea, and this forward checking idea is very simple. It is basically saying that whenever you assign a value, you figure out which values are no longer possible. In fact, you need to do this for the least constraining value heuristic anyway. So, initially you have all the variables and all the values, and let us say we assigned Western Australia red. Now, as soon as we assigned Western Australia red, we remove red from Northern Territory, we remove red from South Australia. We know that there is no way we can assign these particular values. So, therefore, we will not even try the wrong value at all, and we will also detect failure early, as you can see now that when we then assign, let us say Queensland in some order, let us say we assigned Queensland. So, as soon as we assign Queensland green, we are left with, we remove green from Northern Territory and we remove green from South Australia. Okay. This is called forward checking. Whenever I assign a value, anything that is unassigned, we remove the values that are no longer possible. And now, last but not the least, let us say we assigned Victoria blue for whatever reason, we may be going in some order. Let us say we assigned Victoria blue. Now, is this state possible? This state is not possible because South Australia no longer has a value. Why? Because of Western Australia it can't be red, because of Queensland it can't be green, and because of Victoria it can't be blue. But we get to know this because we were doing forward checking. In forward checking we were maintaining which values are possible, and as soon as a variable becomes empty, no value is possible, we backtrack. It is possible that we were doing, we didn't do this, and so we then went to Northern Territory, assigned it some value, we went to New South Wales and assigned it some value, went to Tasmania and assigned it some value, and then came back to South Australia and said, oh, no value possible. Well, that would have been crazy. We would be doing so much search in this subtree, and finally we will come back and say no solution possible at all. Well, we have been able to detect this ASAP. Well, is it ASAP? Okay, so we will come back to that. But at least we have been able to detect it in 1, 2, 3 steps. Now, I claim that you can detect it in 2 steps. In fact, even this state is not possible in terms of finding a solution. Do you guys see this? This is very important. So, if you do not see this, we will wait so that everybody can see this. How many of you think that there will be a solution or there can be a solution from this state? How many of you think there will be no solution from this state? Okay, I see some people who are sleeping, that is all right, but people who are awake should have raised one or the other hands. Anyway, everybody feels that there is no solution here. Why is there no solution here? Now, there is no solution here because at this point both Northern Territory and South Australia have blue, and they both cannot be blue. However, does my forward checking procedure know this? No. Actually, intuitively if you think about it, this constraint between Northern Territory and South Australia is between 2 unassigned variables, and that is actually an important observation. See, up until now in forward checking we were saying I assign something and then I propagate this information to all the unassigned variables and remove their values that are no longer possible. This was propagating the constraint from assigned to unassigned. But now we are saying that we want to even improve this algorithm, and we want to get to a place where constraints between two unassigned variables can be taken care of. We can figure out that, look, this is not possible because they both have the values remaining which are no longer, only one value remaining which is no longer possible, okay, together. In fact, there is an algorithm which is much more interesting, which allows us to propagate constraints between unassigned variables very well, and that algorithm is called arc consistency. Okay. So, this is exactly what the slide says, that NT and SA cannot both be blue, but forward checking would not figure this out. You need to somehow propagate constraints between unassigned variables, and the algorithm that leads us there is called the arc consistency algorithm, and this is the main thing that I would like you to learn today. So, let us say, and so I will tell you how to do this. It will be hard to come up with this in the next minute or two, so I can't ask you a question, but I hope you learn this very well. So, it is not very hard. We say that an arc x to y is consistent if and only if for every value small x of x there is some value small y for y. An arc x to y is consistent if for every value of x there is a value of y. If for some value of x there is no value of y, what can you say? Somebody raise their hand. If for some value of x there is no value of y, what does that tell me? That value of x is not possible, and if that value of x is not possible, we remove it. Very simple. And now that some value of x has been removed, which all arcs might see some more removals? It's a harder question. Other variables z to x. Why? Because for every value of z there should be some value of x, but now I have reduced one value of x. If I have reduced a value of x, it is possible that some value of z which was dependent on this value of x is no longer consistent, and we can remove those values of z, and so on and so forth. This is an inference procedure. Whenever we remove a value, we have proven that this value of x cannot exist. We are not searching, we are not trying it out and backtracking. See, searching is more like, I have many options, let me try this option, oh, it didn't work, let me try that option, oh, it didn't work. Inference says, I have these options, this particular option I can prove will not work, therefore I will go there. And arc consistency is the approach where I enforce these constraints between unassigned variables. Let us take an example. Let us say we are at a point where Western Australia is red, Queensland is green, and we want to somehow propagate this to say that, look, this is not going to lead to a solution. Let us try to just enforce some arcs. So, let us enforce South Australia to New South Wales arc. For every value of South Australia, do we have a value for New South Wales? Yes or no? Yes, please answer, because then I would know you getting it. So, for every value of South Australia, do we have a value for New South Wales? Yes. Can we remove any value of South Australia? No. Okay, fine. This is consistent. But now let us look at it in the other direction. For every value of New South Wales, do we have a value for South Australia? No. For value New South Wales blue, we do not have a value for South Australia. So, we can remove New South Wales being blue. We have proven that New South Wales cannot be blue. This keeps going. Let us say we check Victoria to New South Wales now. For every value of Victoria, do we have a value for New South Wales? For Victoria green, do we have a value for New South Wales? Yes. For Victoria blue, do we have a value for New South Wales? For Victoria red, do we have a value for New South Wales? No. So, Victoria cannot be red, right. and this keeps going. So, basically at some point we will check the arc South Australia, the Northern Territory, we will realize that, oh, for every value for South Australia blue, we do not have a value for Northern Territory, we remove South Australia blue. As soon as we remove South Australia blue, South Australia has no values possible, we have detected failure, we will backtrack. So, in other words, arc consistency detects failures much earlier than forward checking. Forward checking is only enforcing constraints from assigned to unassigned. Arc consistency is enforcing constraints between unassigned. Yes, there was a question.
Is consistency also defined for non-neighboring states?
No. So, neighboring in what?
Like in this sense?
No, not let ask the question in not the map coloring vocabulary. So, non-neighboring in which graph? In the constraint graph. We talked about constraint graphs last time. Very good. So, will we also employ this in non-neighbors in the constraint graph? Well, we have already said that all constraints are binary because we can convert any general CSP into binary CSP. Therefore, all constraints are between two variables. Whenever there is a constraint between two variables, we have added an edge between the constraint graph, between them in the constraint graph, and so they are neighbors. And so, while there may be constraints between non-neighbors, for now we will not worry about it. We will simply check them locally between neighbors, between the two variables which are linked to each other by a constraint, and then keep enforcing it. See, as soon as one value goes down, then its neighbor becomes active and its neighbor becomes active. So, the constraints will propagate. One question you should ask is, will this solve all problems? Can you come up with a problem where arc consistency is not sufficient? Somebody? Okay, so let's look at this very simple problem. I have three variables A, B and C. I have inequality constraints and I give everybody red, green. Now, is there a solution to this problem? Is there a solution to this problem? No. Does arc consistency figure it out? So, let us check the arc A to B. For every value of A, is there a value of B? Yes. So, no problem. Similarly, you can check B to A to C, B to C, everything. Will you ever get a problem? You will never get a problem. So, arc consistency will not get rid of all possibilities, will not detect all failures. In fact, if I want to detect failure here, what do I need to do? No, you can always do search, but inference wise, what do I need to do? So, I need to see that, okay, while A to B, B to C, C to A are independently possible, A, B, C together there is no assignment whatsoever. So, you can think of AB as trying red, green, red, blue, red, green, green, red, 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 green, green possibilities and seeing that some possibility exists. Similarly, in ABC, I can try, red, 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 I can try red, red, green, I can try green, red, green and so on and so forth, and I keep trying and I realize, oh, no possibility exists. And if no possibility exists, then I need to backtrack. So, the extension of arc consistency, which is pairwise consistency, to general sets of K is called, yes, it is called K consistency. I just said, right, K. But of course, each arc takes how much time to check? This is domain D, this is domain D, so each arc will take the time D square. Each arc will take the time D square, whereas each K consistency will check subsets of size K. So, each K consistency operation will require time D to the power K. So, now this is very interesting. Now, of course, k is a constant, but as k increases, you are doing more inference and you are doing more constraint propagation. So, essentially what did we learn in today? We talked about arc consistency. We said that this particular algorithm removes inconsistent values between pairs of variables. So, if I have to check the arc xi xj for each value of x in domain xi, I will check value of y, and if there is no value in y, then I will delete x from the domain xi, and if I delete xi from domain xi, then I will add all neighbors of xi xk to the queue, and I will check the arcs xk xi. This particular algorithm is called the AC3 algorithm, arc consistency version 3, and it takes time. Let us think about how much time it takes. So, each arc consistency algorithm takes d square. Each arc consistency may be invoked d times. Why? Because x to y, when will x to y be invoked? When some value of y goes away, then I will say check x to y. So, each, and how many values of y we have? D. So, d times I may want to check a particular arc, and how many arcs do I have? I have n square arcs. So, overall I have n square into d cubed as my time complexity. Okay. Again, just to remind you, I have n square arcs, each arc will be checked d times and each checking takes d square time. So, therefore, it becomes n square d cube. It can be reduced to n square d square if I do more interesting bookkeeping. So, if I remember the support for each value of a variable, how many values in x were supporting this value, and if the value goes down from a certain below a point, then I invoke that arc, and I even remember which values were supporting, etc., etc. So, if I do a lot of bookkeeping, then I can reduce it to n square d square, which is the best we can do, and that algorithm is called AC. Guess? 4. These are engineers or scientists who are developing algorithms, right? And then there is AC2 also, which is even weaker. Okay, good. So, we discussed the arc consistency algorithm. We also discussed that it will not figure out all failures, because detecting all failures is actually NP hard. Why? Because if I can detect all failures, then I can sort of solve the CSP problem, and CSP problem is exponential problem in practice, right? So, it is an NP hard problem, otherwise you will not be studying it in AI. Now, let us think about what is the final algorithm that we came up with, like the backtracking search algorithm. The backtracking search algorithm says, I am at a node, run arc consistency, make sure some values which are not possible are removed. Then I can't remove any other value. If I can't remove any other value, I do some search. So, I take a best variable, assign the best value, and then run arc consistency algorithm on top of it. Then if I still have some, if there is no failure and if we have not found a solution, then I keep doing this, and at some point either I detect failure, or I have so few values remaining, maybe one value remaining for each variable, that I keep assigning it, and I finally get to my solution. This is a combination of search and inference. We are doing search, we are trying out ideas, but we are doing it intelligently. We are saying that every point I try out an idea, I propagate all information, I remove any possible values that are no longer possible, and then I do intelligent search. So, then I do search next. So, I have divided my work. I have said, okay, when I do not know what to do, I will do search, but when I can do some proving, I will do some proving, and I will keep going back and forth into it. In fact, you can even have an algorithm which is an inferential algorithm, which does not do any search whatsoever. That when it chooses a value, you know there is a solution there. You do not need to backtrack at all. But that algorithm would be exponential. That will be doing k consistency for k equal to n, sort of a thing. So, now you are in this very interesting place where if you do search, you can solve the problem. If you do inference, you can solve the problem. If you do search, it is very, very slow because you are uninformed. If you do inference, it is very, very slow, it is exponential. Both of them are exponential. What do? You combine the two. So, you do a little bit of search and then you do a little bit of inference, then you do a little bit of search and then you do a little bit of inference, and it was found that this would lead to the best solution in general. We have done one other version of this in the past. Somebody make the connection to what we have done so far which is related to this? Very good. What's your name? Ash, again sir. Calculating the admissible heuristic. Earlier we talked about, well, we may not have any heuristic function whatsoever. We will have to do uniform cost search. We can have, so that will be equal to h equal to 0 heuristic. We may have a perfect heuristic, but that will take a long time to compute. We may want to find the best place where our heuristic is polynomial computable, so that it gives enough information, so that the search moves faster. And there was the trade off. Too expensive or too inexpensive heuristics are worse, in the middle is the balance. In the very same way, you can do forward checking, that is not enough. You can do k consistency for k equal to 4, k equal to 5, that will be too slow, because now we are doing d to the power 4, d to the power 5. In practice, guess what people do most of the time? K equal to now this is practical common sense. You may or may not have that yet. You are just third year students. K equal to 2, and for some problems k equal to 3 is what people in practice go to. People are okay with quadratic algorithms for these problems. In some rare cases they are okay with cubic, but they almost never go beyond k equal to 3. Everything else is for theory. In practice, and you will see this again and again, there is a topic we do not do called classical planning. In classical planning, there is again this constraint propagation that happens with the mutual exclusion, and you can do mutual exclusion with 2 variables, you can do mutual exclusion between 3 variables, you can do mutual exclusion between 4 variables, but what mutual exclusion do they do? 2 variables. It has almost become like a common sense rule now for me, that if you have an algorithm which can operate at different levels, operate it at the edge level, not at the triangle or clique of size 3 level, not at bigger sizes, not lower, do edge. This sort of shows up again and again and again. I do not know why, I do not have a theory for this, but in practice quadratic in the context of a bigger algorithm which is expensive works more often than not the best. Vishwajit. Can we detect the possible optimal value of n of a node? Possible optimal value of k? No, but I already told you optimal value. Right. So, you should try some more interesting CSPs and see. I mean, this will require you to go read up some literature, but I am sharing this based on my general experience of problems, and not everybody only solves map coloring problems. There are CSP competitions, by the way. Those competitions have benchmarks. Those variable CSP problems may be of thousands, tens of thousands, 100,000 variables, very complicated problems, but still people only use either R consistency or 3 consistency in practice. Now, I am not a CSP expert to give you the very accurate answer of can we look at the graph and figure out the optimal value of k, but my guess is that my advice to you of trying k equal to 2 or 3 will hold 100% of the time, if I mean 99+% of the time, if not 100% of the time. This is my a priori guess. Okay. So, we have 2 more things to discuss in this lecture. So, we will discuss in the next class, and then we will move on to logic, which is a very important and very traditional field of AI, and that will be the last traditional topic we will study in AI. So, let us stop here.